Okay, so welcome to our review lesson on special right triangles and right triangle trigonometry. And again, this is a review, so this should be all stuff that you've covered in geometry. And with that, let's go ahead and get started. Okay, so first off, let's go into special right triangles. If you remember, this was something, hold on one second. Okay. Um, These were right triangles that we figured out while we were, no, not we, because you didn't have me last year, but when you were using the Pythagorean theorem, the a squared plus b squared equals c squared to find out the sides of a triangle. These two triangles were basically ones that we found out had some special properties or some patterns that can make our lives a lot simpler. So one of the first things that we want to do anytime we're working with right triangles, so that means you have a 90-degree angle, is make sure that you know what the sides are. Probably the easiest side that we want to work with or that we need to figure out is the hypotenuse, hypotenuse, hippotenuse. Basically, there's two ways you can think of that. It's either going to be you think of the hypotenuse as the side that is not touching this 90-degree angle. So if you look at this side right here, that side is not touching this angle, so that's your hypotenuse. Same thing on this side, that's not touching that. And then the other two sides are usually called the legs. Now, if you notice on a 45, 45, 90 triangle, the legs are exactly the same size. That's the result of these two angles being the same sized angles. So these two legs are just legs, while on the 30, 60, 90 triangle, you have two different size legs. So one of them is called the long leg, the other one's usually we just call it the short leg. The short leg's across from the 30-degree angle, the long leg's across from the 60-degree angle. All right, so to get into this, let's go ahead and focus in on the 45, 45, 90 first. So again, there's some special properties that we figured out here. Whenever the angles of any triangle are 45, 45, 90, what we know about these two legs is that they're the same size. So we're just going to use the letter X because we use that to just denote whatever numbers we want it to be. So if that leg is any size, so 10, 15, 20 million, the other leg is going to be the exact same size. Now, it turns out the hypotenuse, we could show this through a squared plus b squared equals c squared, but the hypotenuse is basically going to turn into x times the square root of 2. Or some people write it the square root of 2x. I'll just write it this way for just recognition purposes. All right, so let's go ahead and use this to our advantage. Since this property came up, we saw that over and over and over again. 45, 45, 90s ended up with the same size legs, and then the hypotenuse was x times square root of 2. So here's an example problem. So let's say I gave you a 45, 45, 90. And remember, this little box means it's 90 degrees. And then I gave you, or actually, so first off, that's the hypotenuse. That's your two legs. And let's say I gave you one of the sides. So I tell you this is 8. Now, in order to use this, we have to know what I'm giving you. So that's a leg. So I know that one of the legs is 8. And then normally what's going to happen is you're going to have a variable on one of these sides. And then you just have to find that variable and then you're done. These examples, let's go and just fill in the whole thing so that you just know how to do it. So, but read the directions on the homework and then you'll see what parts I actually want you to find, okay? So if this leg is 8, this other leg I know it also has to be an 8 because they're the same size. If that's x, that's x. To get the hypotenuse, it's pretty easy. You just take the leg and multiply it by the square root of 2. So it's 8 times the square root of 2, and you're done. That's it. So given one of the legs, you can actually find the two other sides. Again, this is different than if you did not know this was a 45, 45, 90 special right triangle. You would need at least two of the sides to use the Pythagorean theorem. With this being a special right triangle, you actually only need one side and you can figure out the two other sides. So that's why these patterns are nice to know. All right, so that's one example where I give you the leg. Now, what if I gave you another 45, 45, 90, but this time I didn't give you a leg, I gave you the hypotenuse length. Could you figure out what the two legs are? So take a little, you can pause the video, see if you can figure that out. And if you came up with thinking around, well, I know that the hypotenuse is one of my legs, so that's your x, times the square root of 2. I basically just got to figure out what this x is, and then I can figure out what these two are. So if this is 11, I should be thinking, okay, what number times the square root of 2 would give me an 11? So that's going to be 11 over square root of 2, because if you think about this, what's going to happen with these square roots of 2's when you multiply them? They'll cancel off and you'll just get 11. So my x times square root of 2 is 11 square root of 2 times square root of 2. So that is going to be your leg down here. Another way you can think of this is if you're given a hypotenuse, I know that I'm supposed to multiply my leg times the square root of 2, but if I want to work backwards, then I can say, okay, well, if this is my leg times the square root of 2, to work backwards, I would just divide the hypotenuse by the square root of 2. The opposite of multiplying is dividing, so to go backwards, you just divide. So take your hypotenuse, divide it by the square root of 2, and you'll get one of your legs. Now, we are not supposed to have square roots in the bottom in your denominator, at least in Algebra 2. It's an outdated practice, but we're still going to rationalize the denominator. I should not have this in the bottom in Algebra 2. So I want to multiply by a fancy one, square root of 2 and square root of 2. And you should get 11 times the square root of 2 is 11 square root of 2. Square root of 2 times square root of 2 is square root of 4. And I messed that up. That should be a 2 right there. Let me see. Yeah, I don't have my drawing tools up. But yeah, sorry, that's a typo. That should be a 2. And then you're going to take that and put it over here. So that's going to be 11 square root of 2 over 2, not 4. Okay, sorry. And so that's the 45, 45, 90. So let's go into the 30, 60, 90 triangle. Similar to the 45, 45, 90, people were doing all kinds of Pythagorean theorems and then figured out, hey, look, there's a pattern happening here. So the pattern that happens with this one is you have your short leg. That could be any number, a 5, a 7, a 9, a 10, doesn't matter. But these two, the long leg and the hypotenuse, can be built from the short leg. So it turns out whatever your short leg length is, your hypotenuse is double that. So if this was a 7, that'd be a 14. If this was a 10, that'd be a 20. If this was an 18, that'd be a 36, okay? Or working backwards, if you know the hypotenuse and it's a 2x, it's double that. You would take half to get to the short leg, right? For the long leg, turns out that you just multiply it by the square root of 3. So if you have your short leg as x, you just do x times the square root of 3. So it's 5, it's 5 square root of 3, 7, it's 7 square root of 3. Working backwards, if you know the long leg, instead of multiplying by the square root of 3, you would divide by the square root of 3 to get back to here. So if this was 10, this would be 10 divided by the square root of 3. If this was 20, it'd be 20 divided by the square root of 3. Okay? All right, so let's see some examples here. You get your 30, 60, 90. That's your hypotenuse. That's your short leg and long leg. And then let's say that I give you one of the pieces of information is that you have a 5. So again, you cannot use the Pythagorean theorem because you need at least 2 sides for that to work. So we're going to use this little pattern that we picked up on. So I know my short leg's a 5. The easiest one to find is the hypotenuse because it's just double that. So that's 5 times 2 is 10. Long leg, or actually this is pretty easy too. The long leg is just multiplied by the square root of 3, so 5 times square root of 3. Now you know all 3 sides of this triangle. All right. One thing too, don't turn this into a decimal. Just leave it as an exact answer. You could definitely do this in a calculator, but you would have to round off. But for now, just leave the square roots on there. Okay. All right. So that's that example. I gave you the short leg. Let's say I gave you, and again, that's a hypotenuse that doesn't touch the right angle. 30 is right there, so this is my short leg. 60 is right there, so this is my long leg. So last example, I showed you the short leg. Let's say that I gave the hypotenuse in this example. So looking back at this framework over here, or this pattern, I know my hypotenuse is double the short leg. So if my hypotenuse is an 8, and something got doubled to make that 8, just divide it by 2 instead of multiplying by 2, and you get your 4. Some mistakes that I see, or a mistake that I see some students make, is that they think the 2x means you're supposed to double this 8 and get a 16 here. But remember, your hypotenuse should always be your longest side of a triangle. So that doesn't make sense that your short leg is 16. Okay. So just kind of use some logic there. Just take half of it to get to this 4. Now, once you have this short leg, that's a 4, it's easy to build your long leg from your short leg. I would not try building my long leg directly from the hypotenuse. You'd have to try to relate this 2x with this x squared root of 3. But if you have your short leg already, just use that. So that's your 4. And then I know my long leg is my short leg times the square root of 3. So it's just 4 square root of 3. No denominators here to rationalize, so that's it. So you got those 3 sides. So I gave you the short leg, you found it. I gave you the hypotenuse, you found the 2 other sides. Now let's figure out with the long leg. So one more example. Hypotenuse, long leg is across from the 60, short leg is across from the 30. And let's say I gave you the long leg this time. So again, I don't want to work from the long leg to the hypotenuse. I usually want to keep referencing back to the short leg, because if you find this x, it's easy to figure out the other 2 from there. So if I know my long leg is a 12 and my short leg is going to be related to that, again, you can think of this like what number times the square root of 3 would give me a 12. And then once I figure out what that number is, that's your short leg. And it's just 12 over square root of 3, because those 2 would cancel. You just get a 12. So this number right here is your short leg. Okay. Or you can just, if you pick up on another pattern, it would just be your long leg divided by a square root of 3 gives you your short leg. And again, we need to rationalize this denominator. We technically don't need to, but all the textbooks tell us that we should, so we'll go ahead and do it. You multiply by the square root of 3, top and bottom, that's your fancy 1. Square root of 3 times 12 is 12 square root of 3. Square root of 3 times the square root of 3 is square root of 9, which is just a 3. Okay, and you get this, so 12 square root of 3 over 3. And you can simplify some more. 12, 3 goes into 12 4 times. So that's going to be 4 square root of 3. Is that simplified out? Okay, now your hypotenuse, now that we have a short leg, your hypotenuse is double this. So if you think of 4 square root of 3 and you double that, you times it by 2, you just multiply this out. Don't multiply the 3 by the 2. This is a square root of 3, not a 3. This is just a regular 2, so you want to multiply by that 4, so you get 8 square root of 3. And those are the 3 sides of that triangle. All right, and that's it for special right triangles. So that's basically how you're going to use those. Next topic we are going into is going to be trig ratios. So trig ratios, if you remember when you went over this in geometry, it's sine, cosine, and tangent are your main 3 trig ratios. Sine of an angle is your opposite side over your hypotenuse. Cosine of an angle of a right triangle, remember these trig ratios only work with right triangles, is your adjacent over hypotenuse, and tangent of an angle is opposite over adjacent. Now it's important to know that anytime you write sine, cosine, or tangent, you need to write a number here. You can't just write cosine and then equals something. It has to have a number or an angle or a variable. It's cosine of something. A lot of times I see students leave this blank. That doesn't make any sense. That'd be like having a square root and not having a number inside. This is a function, so you need to do the cosine of something. So you need something here. Right now that's a acute angle. So these are pretty easy to set up. The main thing is just remembering what goes over what, because that's where most students get mixed up. And you may have heard of SOHCAHTOA as a way of memorizing what sides go with which of these trig ratios. SOHCAHTOA. I like writing it like this. So SOHCA over H, T over A, SOHCAHTOA, just because it helps me remember the fraction part of it. So what I'm going to do is I'm going to go ahead and just put that up in the corner so that we can reference it pretty easily. So if I look at all of these triangles, they're all right triangles. And I know I have to deal with an opposite side. I know I have to deal with an adjacent side, and I know I have to deal with a hypotenuse. So it's your 3 sides of a triangle. Now, you actually know the hypotenuse, and it's always going to be the same. So see if you can take a look at these triangles, and you can figure out where the hypotenuse is on each one. All right, and if you got these, you're correct. Good job. Now, you actually cannot write down what the adjacent or the opposite sides are until you know which angle you're talking about. And with a trig ratio, you're never talking about the 90-degree angle. You're always talking about one of these 2 acute angles. So right now in this first triangle, I don't know which of these two angles I'm going to focus in on because it has to be sine of an angle. I don't know which angle. So you need a certain amount of information for this to work. So let's say that I gave you theta. This is just a Greek letter. It's a variable, Greek letter theta. Normally we use this instead of x when we know it's an angle. Not always, but hopefully you know that. But so this is theta. Um, this can tell me which angle that I'm talking about. So if I'm talking about this angle down here, now I can fill in the opposite, the opposite and adjacent sides. So the opposite side, just like the hypotenuse is opposite of this 90-degree angle because it doesn't touch it, the opposite side right here is going to be labeled because it's the one that's not touching your angle. Okay. The adjacent side is the one that does touch your angle. So that's your adjacent side. Now, technically, this is adjacent as well. By definition, it's adjacent means it's touching it. But that's already reserved to be your hypotenuse because that's across from your 90. So the adjacent, this one's just called adjacent. Now, the reason why I say you got to know what angle you're talking about is because let's say that I wasn't talking about this angle. Let's say that we wanted to work with the other angle. That means that you need to switch up your labels because now this opposite side is touching there. That can't be true. So if your angle switches, your sides are on the other sides, okay? So again, if your angle was here, it looks like that. If it switches to the other side, that's your new labeling, okay? That's why it's very important that you know which angles we're talking about. So take a look at these triangles now. I went ahead and filled in some of the thetas. See if you can figure out where the opposite and adjacent sides are, and then I'll post the answer in a couple seconds. All right, and you should end up with these. All right, so the opposite side is across from the theta, adjacent side touches it, opposites across, adjacent side touches it, opposites across, adjacent side touches it. All right, so that's the labeling of the triangles. And again, you need to know that labeling. That way that you can fill out these trig ratios correctly. All right, so let's work with this thing. Let's say I gave you different sides, okay? So 3, 4, and 5. And I wanted to make sure that you knew which of these trig ratios meant what. So if I ask you what the sine of theta is, you're going to think of so, because sine starts with S. That's going to be opposite over hypotenuse, okay? And then you just fill in the numbers that you have there. So 4 over 5. So sine of theta, when someone says, what is sine of theta? You say, okay, it's 4 over 5 looking at that thing, okay? Next thing is cosine. So if I want to find the cosine of theta, so C-A-H, adjacent over hypotenuse. And then you just fill in the numbers, 3 over 5. Simplify if you need to. These are pretty basic numbers, so you cannot simplify them. Tangent is opposite over adjacent. And then you just put 4 over 3, opposite side over adjacent side. And that's it. That's your trig ratios, sine, cosine, and tangent. At least up to this point. We're going to be using these more as we move on through the chapter. And again, this is just a review, making sure that you know what it's talking about when it says sine, cosine, and tangent. So that is 3 trig ratios, sine, cosine, tangent. Turns out we have 3 more, but they're very closely related to sine, cosine, and tangent, and they are very simple to find. So one's called they're called the reciprocal identities. Reciprocal means that basically you flip it. So first one is called cosecant, CSC. What that is, it's the reciprocal of sine. So instead of opposite over hypotenuse, it is hypotenuse over opposite. And that's it. So once you find sine, you just flip it. You have cosecant, pronounced cosecant, right? Cosine, the reciprocal identity of cosine, it's called secant. Okay. And instead of adjacent over hypotenuse, it is hypotenuse over adjacent. So again, you just flip cosine and you have secant, called secant. And tangent is same thing we've been doing. You just flip it. It's called cotangent. C-O-T, cotangent. And that's adjacent over opposite, and that is pronounced cotangent, right? So those are your 6 trig ratios that you're going to be expected to know. So let's kind of practice this. Let's go back to that example that we had. So we found sine, cosine, and tangent of this triangle. So let's say we wanted to find cosecant. So cosecant again comes from sine. So c cosecant. And then all you're going to do is just flip it. And that's it. Cosecant's 5/4. Same thing with cosine. Cosine goes with secant. So secant theta. And then you just flip it. And last one, tangent, goes along with cotangent. And to find the cotangent, you just flip it. And that's it. So if you have sine, cosine, and tangent, just flip them over. You have secant, cosecant, secant, and cotangent, right? So your problems are going to look a little bit like this. You're going to have a triangle. I'm going to give you two sides on some of them, and I am using x as my variable here. Like I said, normally this is theta, but sometimes you'll see an x. So you got 6, 8, and an angle of x, and you're asked to write all 6 trig functions. Now, first off, I have my sides, but the thing is I need to know all 3 sides for now for this to work, okay, for these type of problems. So I'm going to go back to the Pythagorean theorem. I know 2 sides of a right triangle. I don't know if this is a special right triangle. I have not shown you how to figure that out yet. So just use the Pythagorean theorem if you have 2 sides. So a squared plus b squared equals c squared. A and b are your legs. C is the hypotenuse. It doesn't matter which one you put for your legs for a and b. They can get either 6 and 8 or 8 and 6. Doesn't really matter. What does matter is that your hypotenuse is the one that's isolated on the side. All right, so just fill that in. You got a 6 squared plus 8 squared equals c squared. 64 plus 36 equals c squared. And again, if you mix this up and put an 8 and a 6 here, it would just say 64 plus 36, which is the exact same thing. It's still 100. And then square root both sides. C is 10. Technically, it's plus or minus 10, but since we are talking about lengths, you cannot have a negative length. So that side is a C, is 10. Right? So you found that missing side. Now we can start on our sine, cosines, and tangents. So sine of x. Again, we need to know what the hypotenuse, adjacent, and opposite sides are, so it does help to kind of label those. I'm just typing out the whole word, but you could just put H, A, and O. So again, if your x was over here, that would be opposite would be there, but that's not what the problem said. The problem said this. So let's go ahead and start filling it in. Sine x is, so if we look up here, opposite over hypotenuse. So opposite is 8, hypotenuse is 10, so 8 over 10. Go ahead and simplify that. You get a 4/5. Next up is cosine. That's adjacent over hypotenuse. So it's 6/10. And that simplifies down to 3/5. And tangent is opposite over adjacent. So that's going to be 8/6, which is 4/3. Now for the other 3, cosecant comes from sine, and it's just flipped over. Cosine, secant comes from cosine, and that's just flipped over. Cotangent comes from tangent, and that's just flipped over. And there you go. You got all 6, right? So let's go ahead and do this one. So this one is different than the previous one. The previous one, I gave you 2 sides. You were able to find this 3rd side. This one, I only gave you 1 side. So right away, you cannot use the Pythagorean theorem. And with just this information, we can't do anything. This would not be enough information. But let's say I gave you that angle was 45 degrees. Now, I would have to give you this information. You can't just assume it, okay? So if you're given this information and you're given that this is actually a 45-degree angle, then you know this is a special right triangle that we just used, okay? Because this should add up to be 180, so 45 plus 90 plus another 45 would be with a 180. So this is a 45, 45, 90. And the side that I just gave you was the hypotenuse. So if I gave you the hypotenuse, if you remember, that's x times the square root of 2. So my x must be a 3, which means that these 2 sides must also be 3s. Now I have all 3 sides. So now I can start my trig ratios, right? There's going to be quite a bit of simplifying that's going to be going on here, but the initial or the concept itself should not be that hard. So sine of x is opposite over hypotenuse, so it's 3 over 3 square root of 2. I can see that I have a 3 on top and bottom, so those two are going to, 3 divided by 3 is a 1. So I'm going to It's going to be a 1 over square root of 2. Again, in algebra 2, we do not like having square roots on the bottom. I personally don't mind them, but again, it's an antiquated kind of process. But square root top and bottom, square root of 2, square root of 2 over 2, and you're done. Okay, flip that over, and you get 2 over square root of 2. Rationalize your denominator. You get 2 square roots of 2 over 2. Simplify that. You get a square root of 2, and you're done. Cosine is adjacent over hypotenuse. So 3 over 3 square roots of 2's. I see these 3's right here. Now, kind of look for patterns. I mean, I told you this came from a pattern. It made your life a lot easier. So always look for patterns in math. I got 3 over 3 square roots of 2. I literally just did that right here. So I don't have to go through this whole process because I already know what it is. It's square root of 2 over 2. Now, you could very well just put, since I know that these two are the same, these two must be the same, so that could just be square root of 2. I'm just going to show a little bit of a process here, though. That's flipped over, but I already know that that's going to be that, okay? Because I already did the work here. So if that ever happens inside of one of the problems, I don't expect you to show the work every single time. If you know these two are the same, just write it. You could always do it as a checking kind of way to make sure your answer is right, but otherwise just kind of write it out. Okay, tangent is opposite over adjacent, so 3 over 3. TOA, 3 over 3. 3 divided by 3 is a 1. 1 flipped over is 1 over 1, which is a 1. And there you go. All right. And got 2 more examples here. Let's say I gave you this. Again, this is not enough information to use the Pythagorean theorem because I need 2 sides for the a squared plus b squared equals c squared to work. So I need a little bit more information here. So I'm going to tell you that this is a 60. So this is the given information. Is if I told you that's 60, that's 12, that should be enough that you can solve this thing out because now I know that's a 30. 60 plus 30 plus 90 is 180. Now I know this is a special right triangle, but this is my 30, 60, 90 special right triangle that we covered earlier. So I can find all 3 sides. Remember, the reason why I need that is because I need all 3 sides to do the SOHCAHTOA stuff. So if well, first off, I got to figure out what side this is. Was this the long side, hypotenuse, or the short, or long leg, short leg, or the hypotenuse? Keep in mind it's across from the 30 degrees. So across from the 30 degrees is your short leg. So I gave you the easy one. So your short leg's at 12. So your hypotenuse is going to be double that. So double 12 is at 24. And then to get your long leg, if you remember, if you have your short leg, to get your long leg, you just multiply it by the square root of 3. All right? Got all 3 sides. Have enough information to make my trig ratios. Make sure you know your hypotenuse, opposite, and adjacent sides to the angle you're talking about. So that's going to be this one right here because that's the one that had the variable x, and it's asking for sine of x. So it's talking about this one, not the 30. They're talking about the 30. All this gets switched around. So sine of x, x is up here. So opposite of hypotenuse. So 12 squared root of 3 over 24. Simplify it out. 12 over 24 simplifies down to 1/2. So 1 squared root of 3 over 2. And that's it. You don't have to rationalize anything because it's on the top. Flip it over. Now you got to rationalize it. But you're going to multiply by square root of 3's. 2 square roots of 3. Square root of 3 times square root of 3 is square root of 9, which is just a 3. Do not cancel these 3's. You cannot because that's inside of a square root. Plus it's not a canceling. That does not simplify out either. So that's done. Cosine is adjacent over hypotenuse. So 12 over 24. It's an easy simplification. It's 1/2. Flip it over, 2 over 1, which is a 2. Tangent, opposite over adjacent. So opposite is 12 square roots of 3. Adjacent is a 12. So 12 squared is 3 over 12. These 12s, just a 1, so it's just square root of 3. Flip it over. You got 1 over square root of 3. Don't want that square root in the bottom. Multiply it out, and you get this, right? And that's the trig ratios. So I gave you one trig ratio where you had to use the Pythagorean theorem to find those 3 sides. One with the 45, 45, 90, and this is 30, 60, 90. One more type of problem. What if that's all I gave you? So all I told you was, hey, find all 6 trig ratios, and I'm only giving you one of the trig ratios. 8 over 17. Now, cosecant's pretty easy to get from that. You get 8 over 17 is just going to be 17 over 8. But I need the rest of them too. And I know this comes from a right triangle. So just draw a sketch of a right triangle. Doesn't have to be perfect. Doesn't even have to be the right sizes or anything like that. This is just a tool for you to figure out what all these other answers are. Okay. So using this right triangle, I can fill in some of it. So with the sine of x equals 8 over 17, I know that's opposite over hypotenuse. Now, I can't fill that in yet. Well, I can fill in part of it. Um, I can fill in the hypotenuse, but that's it. Otherwise, I need to know which angle that I'm talking about. So it's up to you, though, because this is what you drew. So put the x on either one of these angles. It does not matter. Just make sure you fill out the sides correctly. So if the x is down there, if you want to put it down there, that's fine. If you want to put it up here, it's fine. Just make sure that you do opposite hypotenuse adjacent depending on where you put this x. So if it's there, it needs to flip around. Oops, flip around the other way. Okay. If it's back over there, then it should be back there. Okay. So just wherever you put that x, that adjacent side follows it. So just make sure that whatever side you decide to put it on, the adjacent side is going to be touching that x. All right, so I'm going to put it down there though. So we got our opposite adjacent hypotenuse. I know my opposite side is 8 because that's on top. My hypotenuse is 17 because that's on bottom. So 8 over 17 should be 8 and 17. Now, I did not tell you this is a special right triangle. So you can't just start saying, oh, that's double that, all that other stuff. And it's not, because these don't make sense with a special right triangle. So if you have two sides, again, you should do the Pythagorean theorem. I only have one of the sides and the hypotenuse, so just plug it in for either A or B, doesn't matter which one, but that C should be your hypotenuse, and then just solve that out. Subtract 64, square root of 225 is 15, plus minus, but there's no minus, so 15 goes there. And now this just becomes just like the other example problems we did. Luckily, there's no square roots, so we don't have to rationalize anything throughout the process. It's just a matter of flipping that over. Cosine is adjacent over hypotenuse. Flip it over. Tangent is opposite over adjacent. And then flip it over. And you are done, I hope. I think. Yes, we are done. Okay. Just a little recap. These are the tools that we used. 45, 45, 90, 30, 60, 90, Pythagorean theorem. These are your trig ratios, nice little neat note page if you need it to help you with the homework. As always, feel free to contact me if you need any help or stop by during my new office hours, which I put on the Google Classroom. Hope everybody's doing okay and take care. Bye-bye.